Hiya folks, the old fossil here.
This house is about 50 years old, back when cable TV was the hot new technology. But the wires are still there, and they haven't been used for at least 20 years. So I decided to try to build a data local area network using it. That cable has nothing else on it, so there's no interference. It ought to be a high quality medium. Making pulse width modulation is easy for an Arduino clone. I've always wanted to use diodes as a temperature sensor. Back when I was in school, they told me the forward drop of a diode is a linear relationship to temperature, and I want to see it work. So I'm going to collect environmental data from around the house and do an analysis and logging on a PC.
Here's the block diagram of what we're trying to build. Both pieces of hardware use the same little modules for power and the Arduino clone and the cable driver. The idea is the collection unit runs 24/7, taking measurements from the sensors once an hour. Every couple of days, the central unit dumps the data and sends it to a serial log file for the PC to analyze. Here's a power module, just a pair of half-wave rectifiers for the plus and minus op-amp voltage and a series regulator to provide the drive voltage for the cable and the Arduino clone. Here's the diode temperature measuring unit. The forward drop of the diodes is put through a gain 20 buffer amplifier and then through a diode limiter network. Since the op amps run from plus or minus pretty good voltage, I didn't want any problem with the op amp output exceeding the Arduino clone limits. Here's the clone and cable driver. The LM339 quad comparator does not have pull-ups, so you notice that the receive line needs a pull-up on pin 11 of the clone. There's only one pull-up resistor shown there as R20 1K. That's the only pull-up resistor. It's in the central data unit, and all the data collection units are a big wired OR configuration. Here's the breadboard of the network, a 50-foot coil of cable TV cable, and the 4 twisted pairs. The diodes are encased in epoxy in the little straw segments. This is the breadboard of a data collection unit. I'd appreciate it if you didn't laugh at my somewhat Rube Goldberg construction techniques. It's clear what the 4 separate modules are: the power module and the cable driver and the diode temperature module and the Arduino clone. This is a data central unit, essentially the same, except it does not have the diode module and it does not have the plus or minus op amp supply voltage. This is the start of the PC analysis program. The 3 pink buttons are Excel command buttons, and they run Visual Basic routines that load the 2 dumps. Start here is where you start from, and the 2176 is the first number of the dump. The difference column is the difference between what the data collection unit sent and what the central unit received, and it's obviously 0. It's a low noise channel. It didn't make any mistakes in any of my breadboard runs. All 757 bits come through perfectly. The green box at the top is the maximum error, which is 0. So the separated button just goes down the list of 700 variables and splits them out into different columns for each different variable.
Sorry about the background noise, but this is summertime in Arizona. That air conditioner will probably run through September. Stand by for 22 pages of Not very elegant C++ code. I hate C++.
Page 1. Greenhouse 54 is the program for the data collection unit. The top part is a description of the polarity of the pulses on the cable and at the CPU because the drivers invert. It measures every hour, but the Metro only has 2048 bytes of RAM, which will really only hold measurements for 4 days. Oh, by the way, there's a thing called every minute mode for test, because you don't want to sit around a whole hour to wait for one set of measurements. If every minute's one, it goes on every minute. Page 3 has two important flags. UID 0 is the assigned unit ID, and every minute is at the 1 or 0, depending upon how you want it to run. Page 5, you have to set the receiver input pin with a pull-up. And at the end of setup here, you attach the interrupts. The main loop just runs time and blink and waits for an interrupt. If 17 pulses are received, it detaches the interrupt and decides whether or not it was addressed to them. Now, the first 17 pulses could come from another data collection unit, and the dump could take about 18 seconds. So change the delay 20 to delay 20,000 to blank out the other unit. Page 8, this is the interrupt handler. It tests the receive pin, and if it's a rising edge, you set the beginning of the pulse, and if it's the trailing edge, you set the pulse width, micros minus t cents. Page 9, the functions sen16 and PW actually write the pulses to the transmit pin. Measure just does the analog read of the analog input pins. Report adds the measurements to the report arrays, and dump outputs them to the serial. Page 14 is time. It counts the seconds for the hours numbers, and oh, by the way, has the every minute test feature on it. Page 16, dump start, uses the send16 function to actually send the pulses. Page 17 starts the central data unit program. Oh, by the way, there's one bug left in the code. For some reason, when you first start up the central data program, the first dump command does not work. I don't know why. I'll fix it. Something that doesn't initialize right. Page 19, you have to have the input pull-up resistor on the receive pin, and the loop just runs time and blink and waits for an interrupt dump. Once the central unit has received all 757 pulses, it detaches the interrupts. Page 21 is PP16 is the interrupt routine. It measures the pulse width of a full integer's worth of pulses. Page 22, sen16 and PW are essentially the same as in the data collection unit program.
So I guess this was basically part 1. I still have to do an accuracy and temperature calibration for the diode sensors. And actually have to install the thing in-house, probably build a better data collection module. That thing looks kind of raggedy. So we'll get back to you. Thanks for watching.